All right, we're ready to roll. We're recording again, so I believe some of you have had the opportunity to listen to or watch the screencast from last time. So I think this worked surprisingly well. The audio quality, I think, was acceptable. So we'll do the same again here. And here's the plan. So it's my opinion that you'll be able to make some progress on reading up on the various design principles on your own, perhaps more easily than the progress that we need to make on the concurrency topics. So I'd like to focus the rest of this class on the concurrency topics, and then we'll see if there's any time left for these other topics. Okay. I will also, during the next few days, post this extra credit Project 6, which is really a little add-on to Project 5. You know, this will be fairly minor, but I wanted to give everybody an opportunity to explore this idea of connecting an app to a cloud-based service. And we're going to be able to do this in a very painless way. And I have an example that demonstrates some of these capabilities. I'm going to improve it, simplify it a little bit, and then I'm going to post the project description accordingly. Okay, so what we saw last time is an example of a race condition, right? So we had the Java examples. Let me pull that back up, and let's see. Let me pull that up here from Bitbucket. Oh, before, yeah, a couple of other announcements. So I slightly refactored the click counter and stopwatch examples in such a way that, let me pull it up, in such a way that you get more syntax-directed editing support than previously. So let me just show this briefly in Android Studio, and you might be able to take advantage of this as you're wrapping up Project 4, right, which is due on Friday. So let me just show this briefly. Okay. So what we saw was, what we had in the past was these various test classes here under source test, and then it would show up like this. So it wouldn't, Android Studio wouldn't recognize that there's an actual package, and then these things, it would recognize that these are Java files, but it wouldn't really include them in the build path. On the other hand, if you go up here, right, so it does understand that source instrument test Java is part of the build path. See, that's why there it shows a package, it shows this Java folder in green, meaning it's a test thing, and it has the test class right up there, click counter activity test, which is the one that runs in the emulator, annotated with a little arrow, means it's, you know, the green arrow meaning it's something you can run, and you can run it through Android Studio, and it'll run in the emulator, etc. Right? And it has the main Java in blue because that's your production code, as opposed to the test code, which is in green. And here it recognizes all these packages and sub-packages, as you can see. And again, here it recognizes these as proper classes, and if you introduce a syntax error there, it will tell you, right? So if I have this click counter adapter and I mess something up like this, you know, so it'll immediately tell me, and it'll underline the class file in the navigation view on the left, right? So here immediately it'll underline this, it'll put a red marker there, etc. Okay. As opposed to down here, if I mess up, if I put extend 1, it doesn't care. That's because this is not part of the build path. So you might wonder, why is this? And it's really because the Android support built into Android Studio in conjunction with the Android plugin in Gradle don't support non-instrumentation tests. So remember, instrumentation tests are the ones that run in the emulator, right, where then you can actually see the stuff on the emulator in this automated way if you're looking at the emulator while you're testing. So it assumes that the only kinds of tests you'd want in an Android project are instrumentation tests, and of course that's nonsense. That's why we're working around, and we had these other tests here, and we had that extra task in the Gradle build file, right? This one here, no, this one rather, right? So we had this extra task where we saw on Stack Overflow that's how you could bring it back, and it's all because of the Android, this Android Gradle plugin, as opposed to the ordinary non-Android Java plugin, which has perfectly fine support for normal unit testing. And like the Hello Java has that, of course, which we've used like for the test 2 makeup credit, right? So how do we work around these restrictions? Well, the idea is, as long as the code you keep in the test section of your code base is really minimal, there's very little you can mess up, where you would need the help of the syntax-directed editor. So therefore, the Roboelectric one, there are restrictions that require you to keep the dependency on Roboelectric outside of the folders that are in the Android Studio build path. So in other words, I cannot move that up there. So this stays. And then what about the others? Oh, the others, it's really, really simple. So we have, so let's look at this one. No, basically just a kind of just a marker, meaning, okay, well, we want this real test class here, default bounded counter test, which I moved without changing it up into main. Okay, but I just want an entry to be there so that in the Gradle unit test, it picks it up. Does that make sense? That's the only reason there's this thing, and it's basically no code, so there's nothing to be messed up, meaning we don't need the syntax-directed editing for this. And then the Roboelectric is also kind of like that. It's a little more involved, right, obviously. But it's very much boilerplate, meaning, you don't really need to change this part, but instead you add more tests here in this class where the actual test methods are defined that we inherit, using the test case superclass pattern. And that one is in main, and you get the proper support. Okay? And now, to avoid this getting too messy, I said, well, let's at least have a test subpackage. So instead of having, let me expand one of them. So instead of having these tests, for example, instead of having this one next to the actual production code, at least there's one additional level of hierarchy here, so that everything that's test code that, because of this kludge situation, is under main, at least it's under a test subpackage. All right, so at least in this way, it's not in the same place as the production code, which is outside of this test subpackage. So in this way, the bulk of your test code has the proper syntax-directed editing support, bless you. So this will give you, I think, it'll make your life a little easier as you're developing the test code. Okay. Any questions so far? Does this make sense? It'll make your life a little easier, so I think it's worth it. So, you can move stuff by dragging it pretty much in your project, if you want to go this route. If you're comfortable with your testing and you feel like you didn't need the support of proper syntax-directed editing in the IDE, it's okay. And you still have to run the non-instrumentation unit tests, so the ordinary unit tests and the roboelectric ones from the command line using Gradle. That won't change. This is really just a kludge, kind of a workaround, this Android plugin shortcoming to put as much of your code base under Android Studio's syntax-directed editing support, with code completion and that stuff as possible. All right. Another quick thing that's worth looking at, so if we look at the abstract click counter activity test, there's a small improvement here, a small little addition, which you'll see here. So it's pretty cute. Remember, so the rotation will exercise your support for keeping the state. For example, if you're playing, you're getting excited, making great progress, level by level, and then a phone call comes in. So you don't want to start from zero right after the phone call. So that, or if let's say you're on a flight simulator, the ones that they have at the Museum of Science and Industry, and then all of a sudden you're upside down, and your device gets rotated. Same thing, although you'd be less likely, obviously, to be playing the game in that situation. In fact, they won't let you take anything. But in any case, so rotation is a good way to ensure that your application saves state properly and restores it properly in the situation where you would expect it to do so, or your users, right? So how do you make that happen? How do you test rotation? Okay, so here, reset should be 0. Increment 3 times. You expect 3 now, right? Then let's force the rotation, and that's how to do it. So you say, let's talk to the activity and say, let's put it in landscape. Set screen orientation landscape, okay? And now let's look at the displayed value, and it should still be 3. And then set it back to portrait, should still be 3, and then we'll, as a courtesy, reset again. All right, so that's how you can test it. Any questions? So this is pretty easy to add, to pretty much any test suite. And again, so Stopwatch doesn't do proper state preservation yet. Click counter does that. Okay, and I heard, so at least one person told me that there's a way to achieve this effect of the way I do it manually here with save instance state and restore instance state, just declaratively by setting some properties, right? So you might want to check that. And if that works for you, that's a better solution than having to do it programmatically. In general, if you're working with a framework, embrace the support that the framework gives you. So, don't fight it. On the contrary, embrace it. The less code you have to write that the framework can perform for you, the more time you have to focus on actual application functionality and quality, and it'll allow you to add more value. The framework is supposed to give you relief, so embrace and take advantage of as much relief that the framework can give you as possible. Any questions so far? Okay. All right, good. I just wanted to make these little enhancements explicit. And I wish I had thought about this sooner with the slight refactoring of the location of the test code. but better late than never. And I know that some of you are doing testing kind of now, as opposed to having done it all along, so it might still benefit you. All right, so that's that. Now, okay, where is that other thing I had? The simple threads example, okay. All right, it thinks that's not an Android, or I mean a IntelliJ project. That's true. So we'll just import it. All right. Simple threads. Let's see if that works. So we can now take a look at this set of topics. Now I get these annoying and this thing, you know, it's a moving target. Okay, here we go. So we looked at this code last time, right? And what we saw. So let's look at this main method. Let's take a little bit more of a closer look at this example, and then go inductively, generalize from there, see what insights we can get out of this. So here's what we're seeing. So we're creating two threads. I'll elaborate gradually on these various building blocks. So we're creating two threads. We're initializing some shared object. Then we're starting the thread. Remember, starting a thread means just spin it off in the background and come right back. Don't wait for it to finish or even make particular amount of progress or anything. Just to spin it off and come right back. That's what the start does. And then the join means wait for it to finish. So it doesn't really matter in which order I do these things conceptually, and in practice it really doesn't matter either. So I spin off T1 and T2. They do their thing in the background, and I could do my own thing in the foreground, if you want to call it that. But instead, you know, so I could do stuff here. I could continue doing stuff. Instead, I just say, well, I don't really have anything to do. I'm just going to wait for T1 and T2 to finish so that the join achieves that. It's kind of like the fork join model, you know, a little bit, that you might have seen in an operating systems class. Although the fork is that additional thing where forking means you're creating a copy of yourself, and then you're maybe branching based on whether you're the original or the copy to do different things. Okay, that's typically the the fork join paradigm. But here we just have the join, so we create explicit threads that do something specific, different from our main method running in the main thread. And then we just say, okay, well, we can do other stuff and or wait for those background threads. Okay? So this is very similar to the timer in the stopwatch example and probably in your project 4. The difference is the timer really gives you a kind of special purpose hidden thread. You don't actually see the thread. You interact with a timer object that manages the thread for you, and you don't need to deal with the nastiness of explicit threads. Explicit threads are quite error-prone. There are various things that can go wrong. But here, we're trying to understand a few things about how they work. So in the default clock model, there's basically this timer object, and you can tell the timer object to schedule a timer task. Brief digression, what pattern is timer task an example of? So, what does timer task do? It allows you to take a few lines of code, or many lines of code, but we program usually with short methods. So we have, if we have a lot of code, that's probably going to be in another method somewhere. So it allows us to take a little bit of code and say, take this code and run it later, once or periodically, okay. But what do we have to do so that we can actually take these few lines of code and give them to the timer for later execution? We cannot just take a line of code by itself. We have to give it something that you can pass around as an argument, meaning it has to be what in programming language terminology is called a first-class value. And in object-oriented languages, first-class values are anyone? What are the first-class values in an object-oriented language? The things you can assign to variables, the things you can pass as arguments to methods. What kind of things do you pass around like that? Yes, but what kind of things are you allowed to pass as parameters or assigned to variables, or do these things, the kinds of things you can do those steps with are the first-class citizens or first-class values in your language. So in an object-oriented language, what kind of things are those? It's a very general answer. Actual objects, that's right. As opposed to, let's say, a functional language where the first-class things you can pass around are functions that don't have to be wrapped inside an object. Okay? So that's the language paradigm thing. And of course, Java, not being a pure object-oriented language, also allows you to pass basic values. That's basically the C subset of Java. I mean, Java inherits from C, C++, right? So it has all of that stuff, so you can pass a number 2 as an argument. So that's why there is, in the context of languages like Java, there's a mention of basic scalar values, like the basic int, Boolean, float, that sort of stuff, and then objects. In a pure object-oriented language, there wouldn't be such a distinction. Okay? So in Smalltalk, so Smalltalk is the classic pure object-oriented language. And then Scala is a hybrid object-oriented functional language, but Scala unifies the syntax for basic values and actual objects. So you don't need to think about this distinction. Same thing for Python. Some other modern scripting languages like that, right? So, okay, back to the question. So popping that off the stack, back from the digression. So we have a few lines of code, and we want to tell the timer task, take these lines of code and execute them. We want to tell the timer, take these lines of code and execute them for me later. So to be able to pass the lines of code, what do we have to wrap them in? Ultimately, in an object. So we can take the object and give it to the timer. So execute this for me after a certain delay, and then recurringly or not after additional recurring delays, etc. The parameterization of the actual scheduling. But the thing is, we have to have an object that we pass to the timer. That object is the timer task, right? So we have the timer. Let me pull it up, actually. Remember more easily. Stopwatch. Default clock model, right? Here we go. Beautiful. So let's expand. See how, I think I mentioned casually at some point, this arrow syntax, this is Java 8 syntax. So in Java 8, so basically what IntelliJ does is it'll make stuff that in Java 7 and before you still have to write in this explicit way. Anonymous functions that in Java 7 and before you have to write as an anonymous object with a method. In Java 8, you'll be able to use this lighter weight Scala-like syntax to write the same kind of thing, okay? And in anticipation of Java 8 support, even though it's not widely used yet, the IDE already supports that. And when it does this, what's called code folding, where it collapses certain stuff so that you can look at it more effectively, it uses some of that syntax. So that's what we saw when we have the plus here, the folded code. And then when we click on it, it gets unfolded, and we see the raw, actual underlying source code. Okay, so here's the timer object. This cannot be a local variable, right? Because if it were a local variable here, we wouldn't be able to talk to it later. It would be no more accessible after the start method returns. That's why it has to be an instance variable tied to the life cycle of the clock model. Okay, so now we say, okay, here's the new timer instance that will be helping us in scheduling this line. Really what we want to say is schedule this event emission, firing the event. This is the one line of code we want to schedule. So we have to say, in Java we cannot pass around a line of code. We have to pass around an object. So the line of code has to be inside a method, which is a method within an object. Therefore, the timer task. So what other interface is timer task similar to? It also has a run method. Well, thread is, again, thread is similar to timer. Thread is for doing work. But here, we're describing the work that will need to be done. Does that make sense? So this is a separation we will benefit from. So in other words, a timer will allow you to execute something periodically. A thread in the background, a thread will allow you to execute something that might take longer than just like a moment, like a very short moment. So firing an event is supposed to take just a short moment. Okay, whereas a background activity might take a long time. Okay, like downloading a file. Okay. So what other interface can you think of that's similar to timer task, that represents maybe something that needs to be executed later? That's the answer to the earlier general question. That is correct. So timer task is an example of the command pattern. That's right. So what other familiar interface is also an example of the command pattern? Well, maybe it's not quite that familiar. So I'm thinking of runnable, right? So runnable, so in a way, timer task, I don't even know why that's there. It might have some things that runnable doesn't have. Maybe some additional stuff like, maybe timer task has, maybe I can override other methods such as, what happens if the task gets canceled or if stuff like that maybe, or if it has time to stuff. I mean, like runnable won't. But over and over again. No, but that's a separate thing from the timer task, right? That's the timer's responsibility. Right. So I'm just trying to understand why does timer require a timer task? Or could it do with a runnable? It's just a matter of familiarizing ourselves more with that API. Maybe it can also take runnable. But the key point is I think we're now understanding, yes, what we have here is precisely an example of the command pattern in the sense that we have a piece of code where we want to say, execute this for me sometime later, okay? And, that line of code itself is not a first-class value that can be passed around as an argument to the component or object, in this case the timer, that's actually going to do that work for me of executing the task. So the command pattern is something that we're using here, where we wrap the code or this task or action or request within a method inside an object, and that object we can pass around. And so the timer says, oh, okay, I got the task now. That's this object. It'll remember that. And then whenever, recurringly, it has this little thread, and the thread will sleep, and then it'll invoke the timer task's run method periodically. So does that make sense? That's how it works. Now, the other thing I wanted to point out briefly before, so this is actually the right path we want to head in to look at concurrency, because this is kind of a very specific type of concurrency, which is these background timers, because our application is still there, ready to receive user input at any point while this timer is doing work in the background. So even though we don't see an explicit creation of a thread, the timer manages a thread for us. All right? So by introducing the timer, there is a thread in addition to our main user interface thread. All right? And that will tie to the discussion, the more in-depth discussion of this whole issue of concurrency control when two or more concurrent threads access a shared data structure where we have to be really careful, as we saw last time. So this is basically the direction we're going to explore some more and try to get a deeper understanding of. Okay, but so just as one more brief digression along the patterns dimension. So there's another pattern that shares a characteristic with the command pattern. So, and it's one that we're by now quite familiar with. So this pattern says, okay, well, I have things that happen once in a while. So, or let's say I have an object that might occasionally want to send out some information or notification or so. And I want to be able to connect to this object, and I want to be told when that happens. Which pattern is that? Observer pattern, exactly. And you see, so if I want to say something like this, I have this piece of code, and I want it to be executed whenever the subject, the object that we're observing, notifies us. I want this piece of code to be executed. So see how similar that is to the command pattern? And structurally, it's almost the same. So we have to wrap that piece of code for the observer pattern, again, in an object, that is the observer object, and we connect it to the subject, which is the object we're observing or whose notifications we want to receive. So structurally, these patterns are the same, but the intent is different. So here, it's basically, here the emphasis is on taking a piece of code and scheduling it for later execution. in the observer pattern, the emphasis is on finding out when an object that we're observing, and that's why that object is called the subject, when that subject sends out notifications. And with the understanding that the subject doesn't need to be aware of the specific identity of the observer, that as long as there's some object connected that has this appropriate observer interface. So, for example, the adapter in our Android apps, we're just connecting specific methods of our choice with the on-click events of the buttons. You know, so to get input from the user interface. The user interface, these buttons don't know about our specific adapter, whether it's a click counter adapter or stopwatch adapter. They just understand, oh, well, you know, I can connect to any method. I can connect the click events to any method in some object. So from that point of view, that other object is the observer of these click events. And that's really the only knowledge that the button has about the observer object. But what's in common is this idea that some code is wrapped inside an object, or first inside a method which lives inside an object for later execution. Does anyone know or has anyone read what that mechanism is called that underlies both the observer pattern, the command pattern, and even in some sense the visitor pattern? I'm not so much looking for a principle, although in a way the OpenClose Principle does play a role with the visitor. It impacts the consequences of choosing visitor, but I'm looking maybe more for more basic programming mechanism, not specifically, not a design principle, but more of a mechanism. And this mechanism is not limited to object-oriented languages. So it's widely used, for example, in earlier graphical Windows systems such as X Windows, X11 and its predecessors. And that was completely written in C, or most of it was written in C, and they still had this mechanism and used it. So encapsulation is more about enforcing an abstraction. So it's a little different. The emphasis, what I'm looking for, is the idea that the idea that you're invoking something later. So you have something, but you don't put it right here where it would be invoked immediately, you know, as part of the sequence of code you're in the process of executing. But you're taking something, you're saying, okay, you give it to some other object or component, so that other object or component can then invoke it later. So what is a synonym of invoking? So you might not have come across this. The term I'm looking for is callback. All right, so you might have remembered now that you've seen this somewhere. But the idea of callback, you know, that you take some code and you wrap it in a function or method, and then that can be, someone else can then call that code later. That's a callback. And, you know, of course, in object-oriented languages, the method or function that you're calling back is wrapped, but it expresses this idea that there is this registration part. So the observer registers with a subject. So that's the registration, and then the callback occurs later. Whenever the subject changes and says, "I'm going to notify my observers." Okay, that's when the callback occurs. And yes, so here the callback occurs when the timer decides, well, it's time to execute the task. Every time it decides to do that, a callback occurs to this run method. So in that sense, this is the same underlying mechanism. And in a way, the visitor has this also because when you pass the visitor to the accept method of the root of your structure that the visitor is going to visit, that's like a registration, like a shorter-lived registration. And then the visitor, every time it looks at a piece or a node of your structure, the structure calls back a method of the visitor, just like we had on the test. Yes?
How many schedules can you put into one of these classes? I mean, if you have different tasks, do you start a new class or can you just put like...
Oh, you mean if I want to have one task that runs every second, then I might want to have another one every minute. You, to my knowledge, for each such series of scheduled tasks, one or more, you need a separate timer instance. So in other words, you create the once every second timer, set that up with a timer task instance for that, and then you create once every minute timer instance, and you schedule that one accordingly with another timer task that would be executed according to that schedule.
But I can still put it inside the same class, right?
Oh yeah, sure. Here you can, if you need 5 different things on different schedules, you can create 5 different timer instances here, and then you schedule each of them. So that you can definitely do.
So it will be under this start call,
okay, so wherever you decide the scheduling should occur. So here, this is kind of tied to the to state transitions in our dynamic model, meaning that start and stop are actions in our dynamic model. So for example, if we go between the stopped state and the running state, the start and the stop methods will be called. So that's how these decisions are made. So you set up the schedule when you want the recurring background execution to start, and then when you want it to stop, you have to make sure you keep around that reference so you can say cancel. Okay, otherwise it's going to go forever if it's a recurring one. All right. Any other questions? Okay, cool. So making progress. Switching back to simple threads. Okay. And looking at this race condition now. So we just looked at this. All right. Now let's look at shared. And remember the following, okay? Where is our command pattern here? Basically here, right? So in other words, each thread is going to do the same, is going to run the same piece of code, but we have to give it to the thread, to each thread as an object, and that suggests there's the command pattern at work, and that is here. So access shared is actually an instance of runnable. So runnable always suggests there might be a command pattern at work here. So there's really only one line of code that gets invoked here, which is this increment. So again, conceptually the idea was, well, we have this shared instance, which just wraps around an int value, and it has an increment method. And the idea is for the two threads concurrently in the background to invoke the increment method that would affect the same shared data structure, which is an instance of the class shared. Okay? Does this make sense to everybody? So we're launching threads 1 and 2. Each of them is going to invoke the same piece of code in no particular order, because we're launching them, spinning them off, and then coming right back. The start method does that. And now they're both launched, and now they're both going to try to make progress on their task, which is incrementing, running this increment method, which is defined below. Does that make sense? In fact, let's tune out. Let's use this nice code folding. Let's tune this out. Here we go. So now we can look at the increment method also at the same time. Okay. Okay. And the increment method, so basically what we have, someone left this open. That's no good. So here, let's say we have a column for thread 1 and another column for thread 2. And each thread performs the same task, which is called access shared, which invokes inc on the same shared object. So in other words, here we have s initialized to 0. And then here we do L1 becomes, or let's call that thing V for value, easier. Okay. Easier to associate with the code. And then V becomes L1 plus 1. And here, L2 becomes V, and V becomes L2 plus 1. Why do I call this L1 and that one L2? They're both called locals there. Because these are local variables in the method, right? So in other words, when T1 invokes inc, it gets its own copy of that local variable, and when T2 invokes inc, it gets its own copy. So there are two different L's, but only one V, right? Because that's a shared, the instance of shared is only one. That's the thing we declare up here. See here? It's a static instance, so that's there only once. We reset it to 0, then the threads operate on it. Okay. And what did we see last time? We saw that sometimes the result was 1 and sometimes the result was 2. So let's focus for a second again on the conceptual side. So conceptually we said we got a shared variable. We have several worker threads, in this case 2. Each worker thread is supposed to increment the shared variable once. And if everything works correctly, what is the only correct result? The only correct result value for the shared variable after each worker increments the shared variable. So each worker increments it by 1. 2 is the only conceptually correct result. That's right. But we didn't see only 2s, we saw some 1s, right? Remember? So that means this program is not what is generally called thread safe. So we did something wrong in the presence of these explicit threads. And even for such a simple situation here, it's very easy to mess something up. So V is, what is it? We saw 1 and 2 in some cases. So how could the 1 occur? I mean, this increments it and that increments it. So here's how the 1 occurs. Here's how the 2 occurs first. If T1 goes first entirely, and then T2 goes next, then, so V is 0, L1 becomes 0, V becomes 0 plus 1 is 1. Now T2 goes, V is 1, so L2 becomes 1, L2 plus 1 is 2, and V becomes 2, and we're good. Does that make sense? So if T1 goes first in its entirety, meaning executes and finishes all of its instructions, and then T2 goes next, we're fine. What about the other way around? Doesn't matter, right? Because they're symmetric, so I mean, it really doesn't matter. They're equivalent. That's right. The problem is when it's neither this way nor that way, meaning this, you know, any kind of situation where instructions from two or more threads are what is called interleaved. For example, this, then that, then this, then that. So let's try that. So initially V is 0. So this goes next. L1 becomes 0. Now L2 becomes 0. Now L1 plus 1 is 1, so V becomes 1. L2 was 0 also. L2 plus 1, 1. V still becomes 1. So you see how one of the increments got dropped because we allowed the two threads to have too much concurrency, too much interleaving, instead of saying, well, one has to finish first and then the other one can go. So in other words, we did not have enough concurrency control, and that caused the program to be not thread safe, which caused the result to be unreliable or unpredictable. Meaning in some cases we had one kind of result, in other cases another, and that is called a race condition, when things could go either way. Yes?
When would that happen? Would they end at exactly the same time?
Well, so there isn't really an exact order or sequence or timing of each of these things, right? Because there might be other things going on and so on. So conceptually, you just have to accept that when you run two threads concurrently, that you will not be able to predict which makes more progress sooner than the other, and you just have to assume any interleaving is possible. Meaning, the only thing that is guaranteed here is within T1, things go in sequence. So obviously, this will never occur before that. Now, that's just sequential execution within a thread. Okay, so this goes first, and then that. Same thing here. This goes first, and then that. So these are never reversed. You know, but let's say within these constraints, any interleaving is possible. So let's count them. That'll give us a better intuition. Because we only have two threads and two instructions in each thread. Okay, we'll count them like this. Okay, T1 and T2. 1, 2, 3, 4, 5, and 6. All right. So that is actually what you would expect. All right. So once again, so T1, either all of T1 before, or like this, or like this, or like this, like this, or like this. All right, so that's your 6. How do you actually understand this more mathematically, and then how do you compute the number of possible interleavings when you have other situations, you know, more threads or more instructions in each thread? So we have how many instructions if T1 and T2 execute, both of them, how many instructions will be executed altogether? Exactly. So that's how you can calculate. So you got 4 slots, right? And you have to distribute these 4 instructions, within these 4 slots in such a way that the sequentiality constraint within each thread is maintained. Okay. So how do you do that? Well, very easy. So you could do let's see. Let's call these slightly differently. So let's call the first one is A and the second one is B. So this one is A1 and B1, and this is A2 and B2. Okay, now we can make sense of this. So we could do A1, A2, B1, B2. Okay. We can do, this is what I indicated with my fingers earlier. So basically the A2 can be here, here, or here. Right? So if A1 is in the first position, A2 could be second, third, or fourth. Okay. A1, I mean A2 rather. Oh, no, sorry, I messed it up. So, sorry. Let's make it slightly simpler. So let's call them, because otherwise I'm going to mess up again. So let's call the one in thread 1 A1 and A2, and let's call this one B1 and B2. So thread 1 is A and thread 2 is B. All right. So if thread 1 goes first, we have A1 and A2, right? And then thread 2 goes next, so we have B1 and B2. Right? If thread 1 starts and then A2 goes in third position instead of second, then how many other choices does thread 2 have? Really only one, because B1 has to execute before B2. So B1 has to go here, and B2 has to go here, right? Okay. B1, B2. And if A1 goes here, and A2 goes here, then again, thread 2 has only one choice, meaning taking up the remaining 2 slots in the right order. And now you can do 3 more with A and B reversed, and there's your 6. And that is, how do you express this mathematically? 4 over 2, the binomial coefficient, right? And that's the 6 that you see here. So you just generalize this when you have more instructions. So let's say you have 2 threads with more instructions. Let's say you have T1 and T2, you have A1, A2, A3, and here you have B1, B2, B3. So you have 6 slots, and you have the same situation. So you have 6 slots. So A1, 1, 2, 3, 4, 5, 6. So A1, let's say A goes first and picks 3 of them in this order, and then B has only one possible arrangement that it can choose. Okay, so that means really it's, how would you express it in terms of the binomial coefficient? 6 over? How many are you picking out of the 6? How many, A gets to pick how many out of the 6? 3, that's right. And that times okay, so this actually with the second factor will make more sense, and then we can generalize it. So A gets to pick 3 out of the 6 initial ones, right? That's 6 over 3. Now there are 3 left, and B gets to pick how many of those 3? 3, exactly. And that's the 1. So there's one choice. So n over n is 1. Does that make sense? So now the beauty is this generalizes, because if we had a third thread, how many slots do we have to fill? we have 9 instructions. So in other words, we have to place these 9 instructions into 9 slots, right, in such a way that the A's go in order, the B's go in order, and the C's go in order. Okay? So the A's go first. So how many does A get to pick? What does A's pick? Let's say A picks this one, that one, and that one. How do you characterize that choice? 9/3, exactly. So we have 9/3. See, so then there's 6 left, so B gets to pick 6/3, right? So that's that, and then that one. So in other words, you would have, if you have, let's see, this one here and that one, right? So you have number of instructions, okay? And here you have the number of threads times the number of instructions, right? Because that's our total number of instructions. Total number of instructions. Okay? That's this number. Okay? And then we have as many factors as threads. Okay? So now I think it's making sense. So the total is you start with, so let's say, oops, I'm going to wrap up, don't worry. So let's say number of threads is K and number of instructions is N. So we have NK over N, and then N K minus 1 over N, etc. And then we have N over N. Okay. So now, so the last one's always 1. Okay. And trust me, so if you go up in either N or K, it gets very large. So where are we getting with this here? So when you look at multi-threading, the number of possible interleavings very quickly gets so large that you don't want to think in terms of individual orderings or individual interleavings. It won't make sense. There are too many. So you really just want to think in terms of, well, each thread just runs sequentially with respect to its own instructions, and they run concurrently with any possible interleaving as long as within each thread it's sequential. Okay? And that's how you kind of make sense of things. And then you understand, well, the way we have to do it is we have to make sure to avoid interleavings for the pieces or sections of the code called the critical sections, where there's access to a shared data structure. That is the key. So in operating systems, they talk about this all the time. You know, but here it's equally important in ordinary app development. So we have to say, well, we will exclude interleavings other than all of A going first and then all of B or the other way around. So meaning that each of these blocks of code have to become small atomic units, so they have to execute in a mutually exclusive way, meaning this has to have exclusive access to V. Then when it finishes, that one, T2, can have exclusive access to V. And the way we can implement this, so this requires so-called concurrency control, meaning limiting the extent of concurrency at certain points in the execution. And the way to achieve this, a typical widely used way, is locking. So we have to have a lock on the shared variable v, and we say, well, T1, before it can access v, has to grab the lock. So one of them wins the lock initially, goes in, puts the lock back, and the other one that might have been waiting will then get the lock. Will get kind of second, will be second in the ordering. So it doesn't matter which, because they're symmetric. So does that make sense? And the way you can introduce locking in Java is using synchronized. So this means we're locking on the receiver object of the method, meaning the instance of the class shared. And then all of a sudden, no more ones. Okay? You can try it out, but that's basically how it works. All right, so lots more things to say, but I don't want to keep you. We'll pick it up here in 2 weeks. So if I'm not mistaken, there's no class next week because of Thanksgiving. So happy Thanksgiving to everybody, and we'll continue staying in touch through the forum. Yes, I certainly will. My pleasure. I will unplug mine and yours, and I will go back to you. No problem. And we're done recording.